Hello everyone and welcome to the next lesson in the data analysis of detector NAND array data. I'm sorry for the delay in presenting this one. In fact, after the previous lesson, I received a number of requests from the people who are analyzing data to explain what we can do when we have a shift in the time reference of the pulsed beam, which takes place from run to run. So when this time reference changes, it is a kind of a shift in the time reference of the pulsed beam, and this causes the all the TDC signals to be displaced compared to what it was in the previous run, and this could complicate the analysis. So in today's video, I am going to tell you how you can deal with this situation. So I got actually the responses over email, and the people who responded immediately were Hardev Singh and Wafia Talsim, and they mentioned that when the data has been actually taken, then from run to run, when the beam has been tuned, there is a shift in the all the TDCs, and therefore to analyze all the files together in the chain the way I have presented up to now becomes not possible, because we have to apply different gates. The T cuts have to be applied differently for each file. So what they really wanted is that the same all these programs should be rewritten. So I have presented the analysis work in the form of programs, root programs, and they want a version of these programs which I am presenting today, in which we don't use T chain, but we actually loop over the files, so that in effect it is like T chain, but then we can use different T cuts for each file. The problem with this approach is that the labor involved in drawing the T cuts, not so much in the T1, T2 that you can do, there will be only one T cut per file in the T1, T2. But in the neutron time of flight versus pulse shape discrimination, you would have to, so there is one gate to be drawn for each detector, and if you have to do this for all the files again, it's a lot of work. So I have got around that difficulty. So in this video, today's video, I am going to show you a shorter way to correct the time shift, so that you don't have to draw the gates, at least in the TOF versus PSD, that those gates for each detector. This you don't have to do for each file, but you have to do it only once in the beginning. So I'm going to present that in today's video. By the way, when you look at these videos, and when you try to, the first time when you study a lesson, the video is probably the best way that you understand what I am trying to talk about. But later on, when you want to refer to the material which I have presented, then you can as well get a much quicker feel about what I have said by looking at the PowerPoint and at the source codes. The source codes will always be available to you for each lesson. It will be packed in the TGZ file, which is part of this lesson at the website. So if you keep a copy of the PowerPoint and of the source codes, then this acts as a good reference material for you, and you don't have to look at the videos repeatedly, which is time consuming. So first thing is that as usual, you can get all the files for today's lesson. It will be packed inside nand05.tgz, which is there in my website. So if you go to the website and if you click on the appropriate buttons which I show here, you can get the help. You can get this PowerPoint also, and along with that, all the source code files for root programs you can get. So today what I'm going to do is, so I'm going to deal with 3 files as an example. So So these are just example files, and so I don't make these files available to you because they are very long. Each file is like 100 megabytes, so I'm not providing these files for you on my website. However, to tell you about this data, so this data was with 50 detectors. Actually, it should have been 48 because two of the detectors, 8351 and 6135, were actually not working in this data set. The name of the tree is Rose Nias, and it has been taken on the Rose Nias system. And the parameters names are a bit different than what I have described to you so far in the earlier lessons, but then they are similar. But then there is also the situation when there are many unused parameters. So after generating paralist.text using the first program, proc001.cpp, then this we used to use for generating the paralist. So you have to do that again. But now we will try to delete the unused parameters. There are many unused parameters, and then you can reorder them so that it becomes similar to what we have been using so far. Of course, you should not change the names of the parameters because they are actually the names of the leaves in the root file. And now if you have a look at the first file which was there in this data set, you can and then I noticed that here the time reference is continuously shifting. You can have a look at this picture here. So you notice that there is many bands, So this is a T1 T2 plot. So this is the timing from one of the MWPCs. So the MWPC1, and I plot the timing of the MWPC1 versus the timing of the MWPC2 along the y-axis. And on examining this data, I noticed that these shifts which are taking place due to the beam instability is happening throughout the run. That means it's not as though you can avoid the first few blocks of data, or you can avoid the last blocks of data and have only one clean band. That is not the case. These time shifts have occurred continuously throughout the data. And at the same time, this data has been taken for a pretty long time. So the user is not interested to discard this data. He wants to analyze it. So we would like to keep the data. And in this particular file, all the data, I think about 95% of the data, is actually concentrated in the band which I have drawn for you gate around. So the fission band is in red, and the elastic scattering or beam-like particles is shown in black as a circle. So if we gate on the fission, you can analyze this data. It will discard the data from the other bands. So this can be done like that, because you will not be missing too much data because the other bands are not very strong. At the end of this video, I shall show you what you could do in case the other bands also are strong. That means if you have taken data where it's not in one band, but a lot of data is in multiple bands, and how do you deal and collect the data from all the bands? This also I will show you. That also is pretty easy. So I'll show you that at the end. This time reference shift, by the way, this occurs, if it is continuous, then generally speaking, we should stop taking the data, and we should request the operators to retune the beam and make it stable. But however, we have to be practical. In practical cases, often we are taking the data in non-ideal conditions. That means we even sometimes that when we observe that there are shifts taking place, but we can't afford to delete or restart the run when already we have collected much of the data. So that's why in practical cases you would face this situation where the data is jumping from one band to another one. So at the end of the lesson, I will tell you what to do if much of the data is not concentrated into one band. But right now, I'm going to show you first how you can analyze the data with just one of the bands which I have highlighted here. The real problem is that these time shifts will also be in the neutron time of flight. So it's not only here that the jumping is taking place, all time signals, because the common time reference is there, they would all show this kind of a jump. So these TDCs, because they are operating in either in common start or stop, and the reference signal is the beam pulsing system. So when you have a phase instability in the beam pulsing system, then you have this situation and this jump takes place, and you get this problem in all the time signals. The thing is that the amount of the shift in nanoseconds will be exactly and precisely the same for all the timing signals. So this is the key point. But however, if you look at it in terms of channel numbers, then that is not the case. It will vary depending upon the time calibration of each of the TDCs. So I strongly recommend the method which I am outlining here doesn't require you to do the calibration. You can work on my methodology which I am presenting here, even if you don't have calibration of all the TDCs. But if you have done the TDC calibration offline, at any point you should do that, either before or preferably after the experiment. Anytime after the experiment you could do it. So this is actually recommended, and it would actually simplify the procedures if there's only one calibrated nanosecond shift. Anyway, so first thing to notice is that if you look at the T1 T2 plot, so I showed you the T1 T2 plot already. So this goes at an angle of 45 degrees. That's because both the time axes are displaced, and the exact same in terms of nanosecond, the exact same displacement takes place, as the calibrations need not be exactly the same. So you might find a small difference, but otherwise this shift propagates like that. So whenever there is a shift, either with more or with less, the time reference shift, then you get. So that's why the tilt here is 45 degrees. Similarly, the different shifts will appear. So when we earlier on we used to run this program number 3, prog 003, we used to run this, and then we have seen in the previous lessons that we get the G pause, that is the position of the gamma rays peaks in all the time of flight spectra, and then we store it in gpause.text. But now when we do this, then you will get different shifts, you will get a different peak depending on which data file you are working on, because the time reference has shifted. So this is the point. But so what I have done is I have rewritten the program, and so all the programs are now rewritten, and they will work for you in this situation. Look at the next file. So I have 3 data files. In the next file, this is the situation. So if I look at the same T1 T2 gate which I had drawn already for you here, if I place that gate, then it doesn't quite work for this next file, and in the third file this displacement could be even more or it could be less, but it all depends upon how much the shift has occurred. So I am trying to show you a methodology by which you can work. Doesn't matter how much the shift is. Okay, so first thing I should tell you is that I have rewritten all the program files. Each of the program files, which are 7 in number, it used to start with prog 001, prog 002, and so on. They are now called as analysis 001, analysis 002, and so on. So these are the programs which you should use if there is reference time shift in the data that you are analyzing. But even if there is no reference shift, still you can use these programs because they are quite general, and I have updated the programs for this, taking into account the possibility of time shifts. So as usual, you have to start with getting the parameter list. So to get the parameter list, you start with this program which I called analysis 001, and this you can run on only the first data file because the parameter list will be the same in all the files. So you run analysis 001 already. So you would have to change in the source code this name to match with your data file name, the first one at that particular beam energy and target projectile system, and then you compile it and then you execute. This will produce the file which is paralist. You can keep the original in some name like that, so as to be able to refer it to it later on, and then make this one where you edit and remove the unwanted parameters, and of course without changing the parameters names you can change the order. So I've done that here. I'll just show you quickly what I mean. So if you look at the original parameter list, it was looking like this, where it starts with P8009 and the MWPC parameters are located here, much nearer the end. I want them to be on the top, so I will move them to the beginning. But also there are several empties, like this kind of thing, which we don't want. And then we don't want to keep the E parameters. We want only the P and the T parameters. So therefore we will edit this file, and again this again is unwanted stuff from here to here. This is called adc04.adc, and in fact the same name repeated, which is not allowed in root files to repeat the leaf name. So all this part we will avoid, and then we don't need these NIAS block triggers which are DAC related. We don't need now in the analysis. So we rewrite, we will edit this file, and we'll make a new file. The new file will be called paralist.txt. You keep the old one in with this name so that you can refer to it whenever you have any doubt. So here is what you should do. This I have renamed. I have sort of reordered like this. I put like what we have been doing earlier. This is easier, if you keep this order, then you can use my codes as it is. But if you change the order here, then you have to change all the source codes also according to whatever order you have done. But this reordering you can do as I have done here. So there are 50 detectors, that's 100, and then there are 10 parameters here which are related to the MWPC. There were 2 non-working detectors also which should have been eliminated. I forgot to do that, but it's better that you eliminate the non-working detectors and then you make the paralist, just as I have given over here. So that's how it goes. And so coming back to my PowerPoint presentation, now after having finished this parameter list, you now know that the next thing to do is to prepare the file list.txt, which consists of the 3 names of the 3 data files. So you do that, and then you start this program, analysis 002. Now this I want you to run as a macro. You should not run it as a compiled program, because I want you to, that is, you should run it in interactive mode, because you have to do some command line work. So what I'm doing in this, compared to what we did earlier, where there was only one T1, T2 plot, because we had written the previous up to now assumed that there is no shift, but now there is a shift. So we are going to draw for each data file. We are going to draw a different gate in the T1, T2 plot. So so this is how you do. First you run the program analysis 002. Once you run analysis 002, you would get 3 canvases. It produces 3 canvases, and on each of the canvas you draw the t-cut. You also, and then from the command line you open work.root. So since this is the first time we are opening work.root, it should be opened in recreate mode. So from the command line you need to type this command, which opens work.root in recreate mode. And then on each of the 3 canvases you draw the t-cuts, and having drawn the t-cut, then you change its name. I have decided to use cut. This is for the first file. For second file I will put 002, then for the third one I'll put 003. That's what I have done. So I rename the cuts, the name of the cut from cut G. This is the default cut name. I change it like this, and then I write it, and it will be written into work.root, so that we can later on use these cuts. So t cuts are to be saved in a work.root file. And then you repeat this so that on all the three canvases which are displayed, and eventually you must close the work.root file. And then if you want to check how much the time reference has shifted, this is what you should do next actually. So you have saved the t-cuts, but you still don't know how much it's useful to know how much the shifting is occurring. So you can do it like this. So these three canvases, when you run this program, analysis 02, then it actually will give you these three canvases, which I am showing over here on my slide. And now you have drawn the three t-cuts. But now if you want to draw in dashed line the t-cut of the first canvas onto the second and third canvases also, and then you want to see how much the displacement is. If that is what you want to do, then this is how you can do it. So after having got the three cuts drawn, let's say you keep them. So this is the picture, but these two dotted lines you want to also draw. So this is the command. So you take the C002. This is the canvas. You know, the CD is used to change the context. So I am changing over to the context to the second canvas. And on the second canvas, I draw the T cut, which is actually drawn on the first canvas. That is called cut 001. I draw it on the second one. So then I get this curve, which you see here in dotted line. And to make this dotted line, you can easily right click on the T cut and then set the line attributes. And that will help you to produce it in dashed line. With the help of this procedure, you will be able to get these three pictures. Which I have shown you over here. This is for you to try and understand how much the time reference shift has taken place. But this is just for your information, not that you really require it in the analysis. Second step is also purely for visualization. It's not a necessary step, but it's good to do it. So you run the next program, and instead of prog 002A, it's now called as analysis 002A.cpp, and when you run it, then you will get to see the all the these histograms which are for the timing channel. And so this is a typical. I've just shown only 4 of them here, but there will be 50 of them if there are 50 detectors. So after having done that, which you can do just for looking at the data, you then go to the next step. Now here is where there is something which I have done which is important. So see, earlier on we used to have this gamma position for one file only. That means we used to combine the data we used to have a chain, and then we look at the entire data set and try to work out. The program used to automatically find out the gamma position and write it in a file called gpos.txt. But now the gamma position is going to shift from file to file because the time reference is shifting. So what I do now is, so this program is written. You don't have to do it manually one by one for all the data files. Just in one go only, all the data files will be examined, and this program, when run, will produce these 3 files. Because I have got 3 data files, so it will produce 3 GPOS files with these names. If you have more, then it will produce more according to the number of data files you have. In each data file, there are these say 50 lines which give the position of the gamma peaks. Earlier on we had only 1, but now we have 3. That means 1 corresponding to each data file, because the time reference is shifting from file to file. So this is the key part. But now that we have got this, we'll be able to do time corrections based upon this data. So that's why it's not necessary to draw the T-cuts for the neutron selection for all the files separately. Just drawing it on one file will be enough. We'll see that now. So let's proceed to the next one. The aim of analysis 4 is to build and then save all the 2-dimensional PSD versus 2F spectra inside work.root. and I don't want to do it one by one for each file. I want to combine the statistics for all the, because this drawing this gate is important. It all depends how nicely you draw the gate. So if you have it with less statistics, then it's not good. So, but at the same time, we don't want to make a chain because the thing is shifting. So analysis 004 does not make a chain. It has a loop going over all the files one by one, but important is this line in the code. It makes another parameter as we go into the event loop, where we define a quantity which is a dummy one called y, and which is essentially this same time of flight is this, detector by detector. It is this particular parameter, but then I put this new term here. So what this term does is that it actually shifts the p values into y, the shifted values in y, according to how much shift is observed in the gamma ray peak positions. So this is the key point which I am trying to make in today's lecture. So this is what you can do. So now the whole thing is that you can now combine all the data in one go. You don't have to look at it file by file. The data is displaced. So so this is what is the trick here. We get the full statistics, and then now we can draw the neutron selection cuts, but it is for the combined data. It is not to be done file by file. And just once we generate the GPOS values were generated file by file, but that was automatic, so you don't have to do anything manually for that purpose. This line, which is part of analysis 4, will take care of shifting the data file by file so that you have a uniformity. And now you draw the t-cut on that canvas where you have this. Of course you have to do for all the detectors, but you don't have to do it for every file. As before, you have to do it for all the detectors, but not file by file. So I think it's important to combine the statistics like I have done here, because you want to have clean data. So also I am going to apply the T1 T2 cut while doing this work. I don't want the randoms which come from the elastics. So what I do is, earlier on I didn't do it, but now I think it's important, so I've included it in analysis 4. In that, we first make a T1 T2 cut, and this changes from file to file, but now we can do it file to file also, because we are not in a chain, we are analyzing in a loop. So file to file we make this appropriate cut in T1 T2, and then we do the shifting of the time channel, because this changes file to file. So in this way we have avoided the randoms to a good extent, and at the same time we have combined all the data from all the different files we have, so that the statistics will be good. And now we draw the t-cut very carefully, because it's very important that the low energy part and the high energy part should be drawn properly, so that we get better moving source fits. That's very important for the final analysis. So this is how you have to save now. So this is similar to what we were doing earlier, but now you see, despite the fact that the time reference is shifting, this plot doesn't show that, because we have made this important part is that we have changed the time parameter like this way with the shift. So now you get uniformity here. So I was trying to say that this is how you will get it on the canvas like this, and then from the root to command prompt you read back all these spectra which have been saved in work.root, and then you draw the these t-cuts on this one by one, and then you save them, and I am saving all of them inside work.root. And so this is an illustration of one of them, and then you simply repeat it for all the detectors. So I was emphasizing the way to draw. So this part which is close to this, these are actually high, this is very close to the gamma. Okay, So that means these are the high energy neutrons. This part. So if you think that you should have drawn rather something like you should have avoided, that's wrong. You have to include this part also. Otherwise, you'll be missing the high energy neutrons. So you must see that you draw carefully, and that's why I wanted statistics. And this part also, this is the low energy part. So only thing is, don't put the randoms in, so where it's very clear that there are randoms. See, this way vertically you can see from the gamma that they're spreading out. These are random, so I don't want to have too much of that. But at the same time, if I were to just block this gate here, that would be very much wrong, because then I would have missed all these low energy neutrons, which are very important part of the spectrum at low energy side for the moving source fit. So please be careful to draw the gates nicely like I have shown over here. Step 6. Now you have to run the analysis 5. Now this is changed from earlier, because what I have done is that I have now made it not as a chain, but going file by file with individual files in a loop, and then I can apply the t-cut for each file. So this is one change, and then you have to change the multi-wire proportional counter calibrations according to your electronics. So this part it was the same as earlier. So there is not much change here compared to earlier, except that I have removed the chaining of the files, and now we are applying different t-cuts in the T1, T2, and then we get. So this is similar to what we have done previously. That is, you get this plot. And here I am showing how you can divide it into 6. So if you divide it into 6 slices, then please put these numbers in slice data.txt as we have done earlier. So this will depend, these values which you see here are not the same as what I had shown earlier in the previous example, because it all depends upon the size of the MWPC, the one which is at the forward angle, and it depends upon the calibrations of the MWPC. So these numbers will change. It depends upon your experiment. So here I am showing an MWPC which goes from, I think, around about minus 5.5 in the x direction to 5. So it's about 11 centimeters in the x, and something like about 5 centimeters, 2.5 or 2.8, I think 2.8 is what I have taken. So that's double of the 5.6. So some height is around 6 centimeters. I don't really know what was the physical size of the detector here. So I just done something based on guesswork. You can put the actual data for your own data. Now we come to the slicing. So this again, the next step, analysis 006. This program is only to check that your slicing is working out. You don't need to do this. It's not essential part of your analysis, but if you want, you can run it, and then you would see that you are able to make the slice cuts just like this. Again, this one I have done without having a kind of a chain. There is no chain over the files. It's run file by file, and then there is a different cuts in the T1, T2. There are different cuts, and then we come to the final step. The final step is producing the neutron energy spectra. So again, here I am avoiding the chaining, and now there is a final trick over here, that how with only one set of cuts for the neutron selection, you are able to analyze all the files where the time calibration, where the time reference is shifting. So file by file the time reference is shifting, but we have only one set of gates for the data. We don't have to draw different gates. How do you achieve that? So that is because, in addition to restructuring this in the way that I have shown, in addition to that, I am going to use while doing the comparison, that is when you try to check whether the event is coming is inside. The command is when you want to see whether the value of the neutron time of flight versus the PSD is coming inside the t-cut. Okay, at that stage what you do is that you just compare it with the displaced value. So I can show that here. So analysis 7 is here. Okay, so the rest of the program is similar to what we had earlier, so I'm not explaining it. The big difference is that now there is a loop over files, there's no chain. Okay, so this is one thing. This is there for all the changed programs. And then the important thing is here when we check the Neutron cut, this one is the T1 T2 cut. Okay, so here it goes file by file, so I can have different fission gate for different file. When we are doing a testing, this is for individual files separate. But now look at this one. So what we do is that again we generate a parameter like this y. So this is not a real parameter, it's a mathematical quantity, and the parameter is this one. Right, this was your time of flight for this particular detector. Detectors are being going over in a loop. That loop variable is idet. So this idet is a parameter, which is a quantity which is inside a loop over here, which goes over all the detectors. And this quantity p, 2 twice idet plus 11, this refers to the time of flight parameter. But now I apply to it this term. Okay, so I get a new quantity called y, which corrects for the time shift. If you look at it for the first file, when I file is 0, then these two terms cancel and you get back the original. So there is no shift in the first file, and from the second file onwards, the reference is corrected to match with that of the first file. And now when I check the is inside command, I don't check it against this quantity, which is what was being done earlier, but I check it against the shifted quantity. So this is the key feature of this. That means you can have only one set of T cuts for neutron selection, and you can apply it for all the files, because we are taking into account in an automatic way this kind of the time reference shift. So this is the part which is for the time reference shift, and I do it here. This is done only while checking this, so I don't make any change in the actual time parameter. It remains as it is. I make this change only while testing the gate, nothing else. So that means when I come to the neutron energy, the calculation remains as before. It is undisturbed. It is just like before, and I don't have to put this quantity y, which is a shifted one. I don't have to put that. I put the original time of flight only over here. So I get the correct neutron energy, because that depends only on the distance between the neutron time of flight against the gamma position for that particular spectrum. So without considering any shifting there, because this is the reference, there is the gamma peak. So this part remains as it is. The change is only while testing that is whether it's inside or not. So this is the trick which you need to understand, by which your labor is saved completely. So that is the main part of the focus of my today's presentation. And the other thing I did is that I also placed all the final neutron spectra not only in this text file which I had done before, because we are going to analyze it with moving source model. That time I need the text file, but sometimes you would like to have a look at all the neutron spectra also. You would like to plot them or have a look at it, so that can be done if you also save it. So I decided to save it inside another root file. I called that root file as neutron spectra.root, and there so this program actually at the end it's here. So this is the part which is saving it in the text file. This is the same as earlier, but now I added this part so that all the histograms are also saved in another root file, and from that root file we can always read it back and display it. So that was all I wanted to really say, except one thing is left out, that is what do you do. Before I do that, so let's summarize. So I'm near the end of what I wanted to say. The analysis of the NAND data, where the time reference is shifting from file to file, does not make it any more difficult to analyze at all. All the programs I have changed for you so that they now are running over a loop of data files instead of a chain. With the when that is done, then you can apply the T cuts, T1 T2 cuts. You have to of course draw the T1 T2 cuts. So this is the only extra labor for you, that for each file you have to draw the T1 T2 cut, and they are different. But the rest of it, like the position of the gamma peaks, is going to be saved in different files. This doesn't require any extra effort on your side, because the program has already been modified and it prepares a different file for each data file, where the positions of the gamma ray peaks for each detector is saved. And the main thing is that the labor intensive work of drawing cuts for neutron selection, that you have to do only once. You don't have to do it for every file separately. This is I think the main key point which I want to emphasize. And then for when you come to building the neutron spectra, again the program is automatically calculating the time reference shift and applying it only at the time, of course, of testing the neutron selection T cut. That's where it's required. So the whole thing goes through, and there is no real problem in doing the data analysis for time shifted file by file time shifts. Now at the end, before I conclude, I would like to say that this situation may happen. See, now I am showing you again what happened in this first data file, that there were many bands. Now luckily most of the data was concentrated in this one outlined band. So we ignored the other band. But what if that is not the case? What if the data is actually distributed in many bands, quite a lot of statistics you have in other bands? You don't want to discard them. So, well, in that case also the same program which I have written will work, no extra effort required. All you have to do is, in your file list, okay, you repeat the same data file name again. So, in the file list we write the names of the files. So in this case, say data 001, that was data 01 was this file. So what you do is you write the same data file once again. You've written it once in the same file list, you write it again. But now when you have a T1 T2 gate for that particular file, you make a different T1 T2 gate. That means first time around you are analyzing the same file, you are analyzing it again, but not with this gate, but the displaced gate. Say this one, you want to analyze this one also. So you draw this gate, instead of drawing it here, you draw it here. And the rest of the thing remains same. So the same file is analyzed repeatedly for all the moving T1 T2 gates. So that's it. I think with the help of this information, you will not have any problem in processing your data which is having these time shifts. So thank you very much for watching, and do get back to me if you have any questions. So thank you again.